Let's enter into a fairly brief synopsis of gravitation theory. The universal law of gravitation, escape velocity, gravitational potential energy, Kepler's laws, those kind of things. So to begin with, we have the universal law of gravitation, which should be understood fairly well by those of you watching this video. For any bodies, we can define it as follows. Oh yeah, there's a polar bear. Offset by your standard issue Kodiak brown bear. And we have their masses, M1 and M2, and the force of 2 on 1 is given by M1G. M1G is mass 1 in the gravitational field of mass number 2. And according to Newton's third, we have equal and opposite force, mass number 2, in the gravitational field of mass number 1. So those forces are equal and opposite. M1G2 is equal to M2G1. And when you measure that force, you discover that it follows an inverse square law, proportional to M1, M2, inversely proportional to R squared. G is the proportionality constant, which is very tiny experimentally. It is an empirical result, this gravitational constant, not a theoretical one. So what about weight? Well, weight is equal to mass times the gravitational field it's in general, mg. And that's force, so that's g mm over r squared. But though that little m is the same for both, so we can make that go away. And what we are left with is an equation for the g field in general of a mass m separated by distance r. That is the gravitational field in newtons per kilogram, corresponds to weight per mass. From this, we can discover the mass of the Earth. Let's solve for m, and assuming that's the Earth, that'll give us gr squared over big G. And since we know we can measure g of Earth at 9.8 generally, meters per second squared, newtons per kilogram, the radius of the Earth is known, the gravitational constant is known. Plug those numbers in, and out pops 5.97 times 10 to the 24 kilograms. The mass of our wonderful planet, 6 trillion kilograms. Now let's check out gravitational potential energy in a varying gravitational field, like movement away from Earth. So here's Earth, and what you're seeing here is the center of mass, or center of gravity of Earth, right here in the center. And radius 1 is a distance from that location, and radius 2 likewise, from the center of mass of the Earth, or center of gravity in this case. What I'm showing here is an arbitrary path of an object moving from R1 to R2. So this is generalized already in that it could be any path, and the results we're going to get are exactly the same. We can loop this object, could loop and go back down around the Earth, and woo, 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 wee, yay, zoo, 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 boink, there. That path was just as valid as any other, and I had fun doing it, by the way. So now here's FG pointing straight down. It points right at the Earth, the gravitational tug. We're going to move the object from R1 to R2, as indicated there, and figure out the work done by gravity. Now, before we go any further, you should recognize, let's see, gravity's tugging it downward. So the work done by gravity, going from here to here, in whatever path, it's going to take an external agent, some effort. An external agent is going to have to do positive work to get it there, because gravity is working against it. So the work done by gravity is positive or negative? It's negative. And it's negative delta U sub G, as we've discussed in past times and circumstances, looking at gravitational potential energy. So now the work done by a force is the integral of the force. across a distance, force times distance, basically. So from R1 to R2 of F radial, we could call it. Now this is an outward force in terms of this equation. In other words, there's this radial force. Outward would be positive. That would be the positive direction of the radial force, away from Earth, where the radii start from the center and move outward. However, we know that Fg is radial inward. It's the opposite direction. Therefore, F radial, the radial force, is negative GMM over r squared. So it's oppositely directed to the radius itself as a vector quantity. Well then, work done by gravity is, this constant comes out, minus GMM, and then we have the 1 over r squared. We're going to integrate 1 over r squared from r1 to r2. And when we do that, we have negative 1 over r, and that negative cancels out this one, so the negative goes away here. GMM 1 over r from r1 to r2 gives us GMM over r2 minus GMM over r1. So that's an important intermediate result, and let's make sure we have the basic concept down here. Remember, when we integrate an inverse square law of force here, this is not force. Notice this r is not squared. These r's are just to the first power. But the work done by gravity and going from r1 to r2 better be negative. So is this quantity negative? Well, the question is, which of these numbers is bigger? R2 is bigger than R1, so this number is smaller than this number. This number here with the R1 is larger, so we're subtracting a larger number. The work done by gravity indeed turns out to be negative from this analysis. Well, we are now ready to discuss gravitational potential energy, because as you know, work done by gravity and gravitational potential energy are very closely linked. Gravitational potential U needs to be chosen from some reference point. And it is arbitrary. We can decide. We usually do so for convenience sake. Now, it'll be negative if it's below that line. Just like if you define the potential energy of an object between the floor and the ceiling. From the reference point of the ceiling, that potential energy will be negative. It's the same thing here. So if we're below the line, it's negative. The logical choice for our reference position may not be immediately apparent to you, but it will be shortly, is infinity. Now, why is that? Why would we choose infinity, which hopefully you're not going to say, but you can never get to infinity. You can never get there. Yeah. I'm glad you guys are taking calculus or have had calculus. So there's a reason for this being the choice, and let's look to see what it is. We know that work done by gravity is what? Well, it's related to change in potential energy. It's the negative change in potential energy, which is U1 minus U2. Now, we've just on the previous slide defined work done by gravity by integrating the force from R1 to R2. When we do that integral, we stick in R2 value minus R1 value, and what emerged from that? But this relationship, GMM over R2 minus GMM over R1. Now I make a big point of that because I don't want you to see this U1 and say, well, U1 is, and you have R2 and then minus U2 and it's R1. Well, this is what we got for work done by gravity. And it is, by definition, the negative change in potential energy, which is U1 minus U2. Now, with that under our belts, assuming we have a belt, let's express what R2 is. Oh, we just did. Yes, it's infinity. So if R2 is infinity, then what's U2? That means that the potential energy at that location is 0. So U2 is 0. And so now we have this expression over here is U1. So let's write that. U1 equals GMM over R2, and R2 is infinity, minus GMM over R1. And of course, the first term is 0. So what do we have? Something very marvelous. Because look at this U1. U1 is associated with R1. So these subscripts are the same, and there's only one term now, so we can drop the subscript and write our general result for gravitational potential energy at some position R. There it is, folks. UG is minus GMM over R. So that's something to keep in mind. That's something to remember. And notice what just happened. By choosing infinity as the reference point, we just eliminated one of these terms. So we really simplified things a lot, with 0 being the potential energy at infinity. Now don't worry if you're thinking, wait a minute, if it's 0 out at infinity, you can't have it be any less than that. And it should be less when you're closer to the Earth. Well, all that is handled very nicely with this, because we already have this negative. So 0 at infinity is the most that UG can be. It doesn't get any bigger than that. But I'll describe that on the next slide a little bit more. So we have FG is equal to negative du dr. Remember, force is minus derivative of the potential energy function. Let's differentiate this function. And if we do that, we have r to the minus 1. You stick the negative down and then raise it to the negative 2 power. And you get GMM over r squared. Just what we should expect to get. So that all works. Now, if we have that the change in r, the difference in position, which is r2 minus r1, is much less than the radius itself. So that would be true for regions close to the surface of the Earth, say from the surface of the Earth to the top of the building or to the ceiling. Then delta r is r2 minus r1. It's much less than r, and the following would hold true. The change in potential energy, gravitationally, from the floor to the ceiling, or say the floor is the reference point, is mg delta r. The delta r in this case would just be the height. So that's just mgh, and that is then the gravitational potential energy, because it was 0 on the floor, so the change is just how much increase there was in going through delta r, which is h. So mgh is u sub g. So that's a practical aspect or version of this more generalized expression. Now I want to explain a little bit more about our infinity reference position and show you why it's so useful for us and in solving theoretical ideas with solar system physics, in the sense that if we want to get something away from the gravitational influence of a planet or a star, this is the physics that will help describe it for us. It's an energy problem. So here we have the Earth. And indeed, we are infinity away with our spacecraft. And the potential energy, since the radius is infinity, the potential energy is 0. Then it decreases toward the Earth. Now we're used to gravitational potential energy going up as the elevation increases, and that is happening. It is going up. It's going all the way up to 0, which is the maximum value at infinity. Less than that, it's an increasingly large number, but it's negative, which is less than 0. We can put the reference position anywhere we want with gravitational potential energy, so this is perfectly reasonable and valid. So it also enables our energy equation to be reduced to a single term. UG is minus GMM over R. Very useful, but it will become more useful than that, as we'll see. So this is nice because the actual energy is based on its position with respect to the center of gravity of the large mass that we're talking about. So anywhere along here, that's the potential energy, just the position. And the other thing it tells us, since this is negative at some r, that if we want to get this to 0, if we want the whole amount of energy to be 0, we have to add a number equal to this number in the positive sense to make it 0. Okay, so let's see what that all means. So if the total mechanical energy is 0, Now, that's what I mean by E here. At infinity, if it's all 0, then we know that it's kinetic plus potential. But potential is already 0 because when you put infinity in there, that's 0. That also means then that the kinetic energy is 0. So for the mechanical energy at infinity to be 0, you've got to not only have the potential energy be 0, but the kinetic as well. So it's out at infinity but not moving. Basically, it's approaching the status of motionless. The gravitational brake is acting throughout all of time and eventually brings it to rest. So this is minus GMM over R. Wherever the spacecraft happens to be, that's the potential energy. But we're going to then we add to that GMM over R, positive. That's the additional energy it must be given to get it out to infinity. So minus GMM over R plus GMM over R is 0, which meets the condition of total mechanical energy being 0. Again, this term, potential. So this term must be the kinetic. This is the amount of kinetic energy an object must be given so that it escapes from whatever position it happens to find itself in. It ends up getting out to infinity with 0 speed. That is the condition for escape velocity, which we'll now take a brief look at. So let's specifically consider the escape velocity. We'll do it for Earth, but this is true in general. And it's just the situation where gravity will never, ever pull it back. It'll never bring the object to rest or halt and reverse its direction and come back to the gravitating object. So here's Earth in all of its massiveness. And a rocket ship blasting off from Earth. That sound is, of course, very important to add in there. Anyway, so here there is some escape velocity. What is that escape velocity? So we shoot it fast enough that it never returns. Well, the total work is delta K, acting on the rocket, and that's kinetic and potential gravitational involved here. And we're actually not worried about the rocket thrusters. Somehow we got to a speed blasting off from Earth here is what we're considering. So K1 plus U1 is K2 plus U2. But if it escapes with the condition that out at infinity it's not moving, then we know what K2 is. And of course, the value of U2 by definition is 0 as well. So it means that in infinite time, the body will arrive at infinity with a speed of 0. So that's the condition. So K1, according to this, is simply negative U1. Well, the potential energy at the surface, because we started this rocket, we blasted it off from the surface, right? So 1/2 mv squared, the kinetic energy that it needs to equal that gravitational potential energy negatively is GMM, GMM over RE. Remember, this is not 0. It's the radius of the Earth, so that's a fairly large distance. So it's not like we're starting at 0, being from the surface of the Earth. So now that little m is the mass of the rocket, and it really doesn't matter. It doesn't matter what the mass is. So we are able to solve for the escape velocity. And here it is, square root of 2 GM over R. You may or may not remember from the past experience or learning that square root of GM over R, this part, is orbit velocity. So it's just the square root of 2 times the orbit velocity. So that's kind of interesting. Now let's see what that actually is. In this case, we have square root of 2 times universal gravitation constant, mass of the Earth, radius of the Earth in meters, gives us 11,170 meters per second, which is 25,000 miles an hour. So that's a really good clip, very fast speed. That will enable the rocket to escape forever from the Earth. But notice how wonderfully easy this was to solve. Total work is delta K. The kinetic and potential at position 1 is the same as at position 2. Now that position 1 could be anywhere along the trajectory underneath infinity, so to speak. And no matter where it is, K1 equals minus U1. It was only at the surface in this case. So we can set these expressions equal to each other, and the radius is whatever position you are at. In any case, then the escape velocity from that position between 0 and infinity is given by this. So the kinetic energy needed is exactly numerically equal to the gravitational potential energy it had at that location with the reversal of signs. So hopefully that is somewhat enlightening, and we'll wrap up this video with that idea and move on to some other concepts.